everybody. Today we're talking about area between curves. So we're going to start with an initial theorem and then we'll kind of make some changes as we go. So we're starting with if f and g are continuous and f of x is greater than or equal to g of x over a closed interval ab, then the area bounded by y equals f of x and y equals g of x, where x is between a and b, is given by the integral from a to b of f of x minus g of x dx. Essentially what this theorem is saying is that we're going to subtract the two functions, but super important is that f is the bigger of the function, so it's kind of like higher in the graph is what we're thinking about. So we want to put whichever function is higher first and then subtract the one that's smaller, so think big minus little. To do that, I'm going to show you a lot of graphs, that way you can see which one's higher, and then eventually we'll take that away and say like maybe you graph it first. So one thing I want you to think about as we're doing this is area. Area should be positive. So this is part of why it's important to set this up correctly, is so that you get a positive answer when you do your integration. So we're going to start with this first little graph. It says y equals 3x plus 5 and y equals 0. So those are my two functions, and we're going to find the area between them and over the interval from x equals 1 to x equals 4. So I want you to look at this graph and notice the 3x plus 5 is this line that has a slant to it. On the bottom, I have y equals 0. So I do want you to see that these are two functions. So the one that's my f of x, this is the big one, so I'm going to call that f. And then the one at the bottom, that would be g of x. So I want to see f is bigger than g. Let's set up our integral. We go from 1 to 4 of 3x plus 5. And then we're going to subtract 0. So that's my f first and my g second. And that's dx. So I can drop the 0 because in this case it doesn't do anything. So I still have the integral from 1 to 4. I have 3x plus 5 dx. I'm using the power rule. I have 3x squared over 2 plus 5 gets an x. I'm going to plug in 4, plug in 1. So I want to show that I plugged in 4. So I have 3 times 4 squared over 2 plus 5 times 4. And then I'm going to plug in 1. So I have 3 times 1 squared over 2 plus 5 times 1. Up to you what you do at this step. You could put the whole thing in the calculator all at once, or maybe you like to do a little step in between. So I'll show that little step in between. So I put in my calculator 3 times 4 squared over 2 plus 5 times 4, that gave me 44. And then the 3 times 1 squared over 2 plus 5 times 1 is 6.5, which gives me a difference of 37.5. So that says this area right here in green is 37.5. So let's look at another example. This time I have y equals x squared minus 16 and y equals 0, and I'm going from negative 4 to 0. So when I'm looking at this picture, what I notice is all of the x squared minus 16 is below the x-axis, and this y equals 0 is where I'm starting. So this is y equals 0. So that's going to be my f of x this time. I want to put it first. And then I'm going to subtract the second one, which will be my curve, which is g of x. So I'm subtracting x squared minus 16, and all of that is dx. So that's from negative 4 to 0. So what I can do to kind of make this easier is drop the 0 and push that negative through. So I have the integral from negative 4 to 0 of negative x squared plus 16 dx. So now I go to integrate. Again, power rule. So negative x cubed over 3. I have 16x. That's from negative 4 to 0. So I need to plug in the 0. It's going to give me 0, but I'm still going to show it just so you see what's happening here. And then I subtract. And careful here, I have so many negatives. So I have the negative for the two areas. I have this negative for the x cubed. I'm going to put a parenthesis around the negative 4, so I hold on to that sign. And then I'll do that again with the 16 times negative 4. Okay, this whole first thing, this is 0. Here's minus, parentheses. This negative is this one. Negative 4 cubed, negative 64 over 3. And then 16 times negative 4 is negative 64. I just want you to see all these negatives. These two negatives, negative, negative, let's make that a positive. So then this negative I can distribute. So I have negative 64 over 3 plus 64. I'm first going to write it as a fraction, which is 128 over 3, because that's the exact answer. And then if I make it into a decimal, then it's going to be approximately 42.67. Kind of watch always when you're doing homework or assignments to see what does it ask for. If it asks for exact, you want to give the fraction. If it says approximately, then you can round it. So our next example, we have find the area between y equals negative x squared plus 4 and the x-axis, and we're going from negative 2 to 2. So this time what we notice is this parabola, our curve is above the x-axis, so this negative x squared plus 4 is on top, and this y equals 0 is on the bottom. Also, I'm thinking you're probably starting to see that sometimes I write y equals 0 and sometimes I write the x-axis. Same thing. So we are going to integrate from negative 2 to 2 of negative x squared plus 4 and then minus 0 dx. This 0, because it's behind the function when I'm subtracting, doesn't do anything. It goes away, so I'm just going to drop it. So I'm going to have negative 2 to 2 of negative x squared plus 4 dx. Right. Integrate again with the power rule. I have negative x cubed over 3 plus 4x. This is negative 2 to 2. So I'm going to plug in 2. There's negative 2 cubed over 3 plus 4 times 2 minus, I'm plugging in negative 2. So again, careful with the negatives. I have negative 2 cubed over 3 plus 4 times negative 2. This is negative 8 over 3 plus 8 minus, this negative 2 cubed is negative 8, but this other negative makes a positive 8 over 3, and then 4 times 2 is minus 8. This time I showed you all these steps to show you the symmetry really that's happening here. I have negative 8 over 3 plus 8. I have minus 8 over 3 minus 8. When I push this negative through, you'll see I have the same thing twice. So this is just kind of double up. So it's kind of interesting to see because it's symmetric. You can see how it's on the left is the same thing on the right. Again, I'm going to write this as a fraction first. So this is 32 over 3 when I add these all together. And then if you want to say approximately, it would be approximately 10.67. Right, so let's try something that isn't just the power rule. Here I have y equals e to the negative 1.4x and the x-axis from negative 1 to 3. So we're starting with the x-axis, which is y equals 0, is my top function, and underneath I have the curve negative e to the negative 1.4x. So my integral from negative 1 to 3 is 0 minus negative e to the negative 1.4x dx. So that 0 has to go first. So this negative will become positive. So I have negative 1 to 3 e to the negative 1.4x dx. I'm hoping you remember we have a little shortcut here for this integration. I gave you this e to the kx dx is equal to e to the kx over k. So I can make this integration negative 1.4x divided by negative 1.4, 3, negative 1. So I'm going to plug in the 3, e to the negative 1.4 times 3 over negative 1.4 minus, plug in negative 1, e to the negative 1.4 times negative 1 over negative 1.4. I'm going to throw this all into the calculator. I'm not going to leave the e at all. I'm going to go straight to an approximation, and I want to show you this twice. I'm going to plug this into my TI-84 calculator first, and then I'll plug it into Desmos just to kind of show you a comparison of how you plug it in. So the thing to watch when I'm using the TI is that it knows an exponential function is going to put things into the exponent. So I have negative 1.4 times 3. And then I kind of just push out of the exponent, and then I divide by negative 1.4. And then I'll subtract, I do it again. So I have e to the negative 1.4 times negative 1, and then divide by negative 1.4. Okay. We're going to call this 2.89. It was 2.88586, right? So let's just make that 2.89. Let's compare in Desmos. So in Desmos, if I start putting an E and I put in negative 1.4, and if I hit times 3, the 3 came down. So I need to go back and put parentheses. And then I can divide by negative 1.4. And then I can subtract E to the negative. But this time I know ahead of time, go ahead and put in the parenthesis, negative 1.4 times negative 1, and then divide by negative 1.4. And again, we got the same 2.89 as our approximation. So just thinking order of operations for whatever technology you're using, you have to be careful with. So here is 2.89. So our next example doesn't fit our original theorem where it talks about the function always being above the other. And so what I see here is I have a function negative 3x, and then I have the x-axis. And part of the time, the f of x is above the x-axis, and part of the time, the f of x is below the x-axis. So we're going to treat this as two separate pieces. In the first piece, which is going to go from negative 2 to 0, I have the negative 3x first and the 0 second. And then in the second piece, which goes from 0 to 3, the x-axis is first, which is 0, and I'm subtracting negative 3x. There's my dx. The two together, we're going to add. So I say the area that was above plus the area that's below gives me my total area. So let's kind of make that look a little better. Negative 2 to 0, the negative 3x minus 0 can be a negative 3x dx, plus 0 to 3, I'm going to drop the 0 and I'm going to put the negatives together. So negative negative gives me a positive 3x dx. So integrate. I have negative 3x squared over 2, negative 2 to 0, plus 3x squared over 2, 3, 0. So let's plug in the 0 first, which negative 3 times 0 squared over 2 is 0, minus negative 3 times negative 2 squared over 2, plus, I put in 3. So 3 times 3 squared over 2, minus the 3 times 0 squared over 2 is just 0. So this negative negative, I'm going to make that a positive 3. Negative 2 squared is 4. Divided by 2, plus the second part, I have 3 times 3 squared, so that's 3 times 9 over 2. So we can write this as a fraction as 39 over 2. If you want to, you can write this as a decimal, and it comes out nicely as 19.5. There's no repetition there, no rounding needed, so either one of those would be right. All right, the next one I have y equals x squared minus 4 and y equals 0 over the interval from 0 to 4. So again, I see this split where part of the graph is below the x-axis, part of the graph is above the x-axis. So let's kind of start below. So below, you can see that goes from 0 until 2, and we're just going to count it over that we can see it. So from 0 to 2, and what comes first is the 0. The x squared minus 4 was underneath the x-axis, so it goes second. We know we're going to add this, and that's going to go from 2 to 4. And in this case, the x squared minus 4 is first, and the 0 is second. So we can make this look a little bit better. This goes 0 to 2. I can drop the 0. I can push through the negative, so I have minus x squared plus 4 dx. And then I can do the same thing here, 2 to 4, just drop the 0. I have x squared minus 4 dx. So I'm going to integrate. I get negative x cubed over 2, actually over 3, plus 4x, 2 to 0. I have x cubed over 3 minus 4x from 4 to 2. So let's plug in 2. So this becomes negative 2 cubed over 3 plus 4 times 2. And then the 0, I'm just going to write minus 0, plus, I put in 4, so I have 4 cubed over 3 minus 4 times 4, minus, plug in 2, 2 cubed over 3 minus 4 times 2. The first part, this becomes negative 8 over 3 plus 8, plus I have 64 over 3 minus 16 minus, this is 8 over 3 minus 8. You could just go ahead and put that all in the calculator. I want to show you for this one what would happen if I didn't split it. Like if I didn't go through and make this into two pieces like we did. So what if I just tried to do the integration from 0 to 4? So this is just, what if I had have done 0 to 4 of x squared minus 4 dx? So we would integrate the same, x cubed over 3 minus 4x. We would have 4 and 0. So we would have 4 cubed over 3 minus 4 times 4, and then the 0 would be nothing. And that would give me 5.33. And what I want you to see is how different that is. So in this case where I got 5.33, it subtracted the positive area and the negative area. So the negative with the positive gave me that smaller number of 5.33, which is why it's so important to split these up and to add the areas instead of just trying to integrate the whole thing. This next one, a couple of big changes. Number one, I didn't graph it for you, and I didn't give you a closed interval. So what we have instead is I want the area bounded by y equals 2x squared and y equals 32. So let's kind of do a little sketch, just an easy sketch. Y equals 32, let's call that y equals 32 up here. And then if I think about 2x squared, it's a parabola. The vertex is at the origin and it would be going up. So what I want you to see is they would intersect and I would have this area trapped between the two functions. So that's important to see. This is what we're going to do. So the bounded will be, there will be intersection points. So let's find those. So 2x squared is 32, says x squared is 16, which says x is plus or minus 4. So this is my 4, this is my negative 4. So those are the bounds, negative 4 to 4. Then I can look at it and I can see the line at the top, which is 32, would go first, and then I would subtract 2x squared dx. So integrating, I get 32x minus 2x cubed over 3. We're going to put in 4 and negative 4. I think we kind of know, we've seen this earlier, that we should expect like some symmetry here. The left and right should be the same. So I have 32 times 4 minus, I'm going to write this as 2/3 of 4 cubed, minus, same thing, now put in the negative 4, so 32 times negative 4 minus 2 times negative 4 cubed over 3. The first part gives me 256 over 3, minus, the second part gives me negative 256 over 3. So these two numbers are the same. The minus minus ends up being plus. So we can write this as 512 over 3, or we can say that's approximately 170.67. So same idea. This says bounded. So we're thinking we have two things. Again, I'm just going to do a quick sketch. X squared plus 1 is a parabola that got moved up 1. Negative 5x plus 7. This is a line, so it has a y-intercept of 7, and then it has a slope of negative 5. So it has this kind of look. So what we want to do is like look for the intersection points first. So I have x squared plus 1 is negative 5x plus 7. I'm going to bring this over. So it's x squared. This is plus 5x, and the 7 comes over, becomes minus 6 to 0. So I factor. So my factors of negative 6 that are 5 are 6 and 1, positive 6 minus 1. So x is 1, x is negative 6. So you can tell my picture's a little off, but that's okay. It just gives us where do we go, where do we go. So I have the negative 6 that's on the left, I have the positive 1 that's on the right, but it gives us a good idea of what's going to happen. So we know we need to integrate from negative 6 to 1 of what's going to be on top. I can see the line is on top. So this is negative 5x plus 7, and then minus x squared plus 1 dx. If you're not comfortable doing that, like if you're not crazy about trying to graph that yourself, you could of course graph it, like let's graph it in Desmos so I can show you how you could do it alternatively. So you want to enter those as two separate lines. So we have y equals x squared plus 1 And then my second one, I have y equals negative 5x plus 7. And you can't quite see it yet, so I'm just going to kind of move it around a little so we can get that all in the frame. Okay, so now I can see when I click on the graph, it's going to tell me here's one point, it's at negative 6. And here's the second point, which is at 1. So this would show you the graph. You can see the intersection points. So you could do this like graphically instead of algebraically to get the bounds. And then I can also see the line is on top and the curve is underneath. So either one of those ways works for me. Before I integrate, I do think I can just make this a little bit nicer. So I have negative 6 to 1. I'm going to keep this negative 5x. The 7, I see this minus with the 1, so 7 minus 1, this will be plus 6 minus x squared. So just having one less term I think is helpful. Integrating, I get negative 5x squared over 2. The 6 gets an x. X squared becomes x cubed over 3. I plug in 1, I plug in negative 6. So at 1, I have negative 5 times 1 squared over 2. I have 6 times 1. I have minus 1 cubed over 3. Let's put big parentheses. Same thing, go ahead and plug in the negative 6. So I have negative 5 times negative 6 squared over 2 plus 6 times negative 6 minus negative 6 cubed over 3. I'll give you two numbers here. I'll give you the first parenthesis and then the second parenthesis. So this first set is 19 over 6, and the second part gave me negative 54. Okay, so I put that together, 19 divided by 6 minus negative 54. As a fraction, that's 343 over 6, which is about 57.17. Let's try some applications now. An amusement company maintains records for each video game it installs in an arcade. Suppose that C of t and R of t represent the total accumulated cost and revenues in thousands of dollars, respectively, t years after a particular game has been installed. If C prime of t, which is the marginal cost, is 2, and R prime of t, the marginal revenue, is 9e to the negative 0.3t, find the area between the graphs of C prime of t and R prime of t over the interval on the t-axis from 0 to the useful life of the game and interpret the results. All right, so we talked about useful life before, and we said to start, we need to look at where is R prime of t equal to C prime of t. I'm going to show you this twice. The first way is I will do it algebraically. So I have 2 equals 9e to the negative 0.3t. To solve this, I would divide by 9, so I have 2 over 9 is e to the negative 0.3t. And then I would take the natural log, so natural log of 2 over 9 is the natural log of e to the negative 0.3t. So natural log of 2 over 9 I keep, natural log of e to the negative 0.3t is just negative 0.3t. So we divide by negative 0.3. So I'm going to show you this in the calculator. That way I can show you two things. So I'll show you what we get as an answer, and then I'll show you another choice of how to solve this. So let's start with, in the calculator, if I have the natural log of 2 divided by 9, and then I divide that by negative 0.3, it says it's about 5. So we're going to use 5 because this is years. Look how I did that. I put parentheses around the 2 over 9 because I want to say only that part is the natural log, and then after I get that number, I'm dividing by negative 0.3. Now, if you don't like that, if you don't like the algebraic approach, we could also do an approach is like let's graph it. So I'm going to type y equals 2. That's going to represent the marginal cost, and then I'm going to put in the y equals 9e to the negative 0.3x, right? And that way I can graph the two, and I could look for the point of intersection. So I'm going to zoom in a little bit so you can see, and I'm just going to click on it and see that 5.014, that's the same number. So I can see either way I get that the useful life should be 5 years. So we found out that t is equal to 5. Now we are ready to integrate 0 to 5. Let's go back to the picture just quickly, because what I want to see is over that time period, which of the functions is on top. And so when I'm looking, here's the curve that's on top and the cost is down below. So the revenue above the cost, which is what we want. If you think about when we look at profit, profit is revenue minus cost. So it makes sense that it came out that way, that the curve was first. So I have 9e to the negative 0.3 t minus the cost, which was just 2. And this time we want to say dt because that's our variable. So we're looking at time. When I integrate, I'm going to use that trick. 9e to the negative 0.3t, I divide by negative 0.3 minus, this will be just 2t. I put in 5, I put in 0. So we'll start by plugging in 5. I have 9e to the negative 0.3 times 5 over negative 0.3 minus 2 times 5. This time, really important to keep that 0 because e to the 0 is not 0, so I need this. It's going to give us a value. And then the 2 times 0 will be 0, but you really need to keep the zeros when you have an e. So I'm going to plug this all in my calculator at once. I got 13.3. I'm going to call it 1. After that, like we're almost done, it says interpret the results. So what would the results tell me? Well, the big clue is this that I said up here, that when I subtract revenue minus cost, it gives me the profit. So what did we find? So what we found is the profit over the useful life. It's important to say that the profit is in thousands. So this represents $13,000 of profit over the 5 years. So I have one more application for us. So using production and geological data, the management of an oil company estimates oil would be pumped from a producing field at a rate of R of t is 100 over t plus 10, where t is from 0 to 15. R of t is the rate of production in thousands of barrels per year, t years after pumping begins. Find the area between the graph of R of t and the t-axis over the interval from 5 to 10. Interpret the results. So kind of we have this idea of what we're supposed to be doing. We're supposed to be integrating, and we can see the bounds there from 5 to 10. So let's go ahead and write those bounds of 5 to 10. This is the area between R and the t-axis. So here's the t-axis. It's just like looking at x. Luckily, this 100 over t plus 10 says, hey, you're at a minimum of 10. So we don't have to worry about that. We know that the R of t is going to be above. So even if I don't graph it, I know R is going to be above the t just from looking at this plus 10 over here. So we are going to integrate 100 over t plus 10, and then you could do minus 0 dt. So I'm immediately going to drop the 0, but it does show us that we thought about it first. We didn't just jump and start to do our integration. So we have 5 to 10 of 100 over t plus 10 dt. So the only part that makes this one tricky at all is this t plus 10. When you go to integrate, you probably want to think about u substitution. So the u would be equal to t plus 10. And then du would be equal to dt. So at least it matches up really well. So I can see I have a dt, I have the u, but remember how we switched the bounds? So when t was equal to 5, the u is going to be 5 plus 10, which is 15. And when t is equal to 10, u is going to be 10 plus 10, which is equal to 20. So now I'm going to go from 15 to 20 because we've changed the bounds. The 100 stays the same, this is over u, plus the 10 stays the same, and this is du. When I integrate, 100 over u becomes 100 natural log of u. The 10 gets a u. This goes from 20 to 15. So we're going to plug in the 20. I have 100 natural log of 20 plus 10 times 20 minus 100 natural log of 15 plus 10 times 15. The expectation usually is once I have a natural log, I'm probably going to get a decimal. So I'm just going to go ahead and plug the whole thing in my calculator at once so I don't have to worry about the decimal. I got a total of 78.768, so I'm just going to call it 77. All All right, so that's the end of this lecture. Next time, we're going to stay with this idea of finding the area between bounds, but we're going to do something called consumer and producer surplus. So it'll show you another really big application to finding this area and to me, like really culminating of what we've been trying to learn this semester.